Okay, a sealed cylinder contains 1.2 exponent 24 helium atoms at initial pressure 1.04 exponent 5 Pascal. The cylinder is then heated until the final temperature and the change in the internal energy of the helium gas are 315 Kelvin and 1.6 exponent 3 joule respectively. The molar mass of the helium is 4 gram per mole. Calculate the density of the helium gas, the final pressure of the helium gas. Okay, this question seems a bit complicated, but we still can do. Yeah, the trick is always put down all the information here systematically in like tables, point forms. Yeah, always gather the information first. Yeah, what we can see from here. But the first thing I want you to pay attention is this word, sealed. It carries a very important meaning here. What is meant by sealed cylinder? Can you imagine what is sealed cylinder? That means it is closed cylinder, right? A closed cylinder. So this cylinder is fixed in volume, sealed. This is the key of it. Yeah, sealed cylinder means it's constant volume. You can say this is isochoric process, yeah, or what? Okay, constant volume. Sealed cylinder means constant volume. This is the first thing we know. We must know this. Sealed cylinder means constant volume. And then here he give us a total atoms. Total atoms, total helium atoms. It is helium. Helium means is monoatomic. Monoatomic, which is this is the one. The degree of freedom is just 3 maximum. Yeah, monoatomic helium is a inert gas, so it's monoatomic. The degree of freedom is only 3. Only 3 degree of freedom. And then initial pressure. This is the initial pressure. Put as P1. It's in Pascal. Good. In SI unit already. Very good. No need to change. The cylinder is then heated until the final temperature and the change in internal energy of the helium gas are this one. So this is the final temperature. So this is T2. And here you see there is a word change. Change in internal energy. So this is the change in internal, change in the internal energy. So this one is delta U, not the U only, is the delta U. Yeah, change in internal energy. Okay, and then we have molar mass of helium. Molar mass. This is molar mass, mass per mole. This one is a gram. You need to change to SI unit. Yeah, need to change to kilogram per mole. That means you need to divide by 1000. Okay, this is molar mass. Molar mass, mass of 1 mole. Calculate the density. So we need to find the density. We need to find density. And then finally, we need to find final pressure, P2. Okay, of helium gas. So how are we going to do this? I suggest you, here you have two conditions. Yeah, we have first condition and also second condition. So I always like to, gather the information in 2 columns if you have 2 conditions. Understand? This is my practice. Yeah, this is my practice. I suggest all of you follow the same way. Yeah, follow the same way. Okay, so let's do it. Yeah. So all right. So okay. So for condition 1, we have pressure 1. Write down first. Pressure 1. It is 1 point. This is my practice. I always like to gather information first. Yeah, rather than straight away solve the question. Yeah, because I'm a systematic person. Are you? Are you a systematic person? Okay, you need to ask yourself for that. Okay, so this is pressure 1 and volume constant because it's sealed, right? So we can say V1 equal to V2. It's just that we don't know the value yet. Okay, we have the final temperature, right? We have the final temperature. So we have T1, we don't know. Okay, we don't know about this. But we have T2, final temperature, which is 315 Kelvin. You see, you have information more systematic. You can solve the question easily. Okay. We have the total atoms. The total atoms should be the same because it's a sealed cylinder. There's no extra helium coming from entering from outside. Yeah, this helium atom also cannot escape to anywhere. So the total atom is the same. Yeah, and I think they are the same is the same atoms. Yeah, N1 is equal to N2. We know this value is 1.2 exponent 24 atoms. Yeah, they have the same total atoms. And what else we know about them? The change of internal energy, molar mass. Okay, write down the molar mass somewhere. Okay, maybe I write over here. Molar mass. Molar mass of the helium. Okay, molar mass of the helium is right. How to write molar mass? Molar mass of helium. Yeah. Okay. It is 4 gram per mole. We need to change that. Change to divide by 1000. Change to SI unit. Divide by 1000 is 0.004 kilogram. Yeah, kilogram per mole. Must always change to SI unit. Divide by 1000. So is 0.004 kilogram per mole. Okay, we got it. Next, we want to find density. So how are we going to do this? How are we going to do this? Okay, so don't worry, do it step by step. Yeah, give us the change of internal energy, right? Make use of that change of internal energy. Okay, write that over here. So the change of internal energy is 1.6 exponent 3 joule. Okay, change of internal energy. So what's the formula of internal energy at first? Yeah, internal energy for helium gas. Okay, if you look at the formula, what's the formula for internal energy? Okay, FO2 NKT or FO2 nRT. Or we always start from the concept of one molecule of gas of 1 degree of freedom. The energy start from half kT, isn't it? Okay, let us start from the most basic one. Okay, so the internal energy of gas start from half kT. This is for 1 degree freedom of one molecule. Okay, now you have what? You have how many molecules? You have many molecules, isn't it? You have n molecules. N molecules. So you multiply by n. And you have how many degree of freedom? You have more than 1 degree of freedom. You have helium, which has 3 degree of freedom. So you multiply by F. Put F first. So that's why the internal energy of gas, the formula become FO2 and KT. Understand? FO2 and KT. That's the formula. And then for helium, internal energy of helium is the degree of freedom. Degree of freedom is 3 for helium monoatomic. Isn't it? Monoatomic. So it becomes 3/2 and KT. That's for internal energy for helium. Next, delta U, change of internal energy. If you want to find change of internal energy of helium, then what changes is the temperature, isn't it? N/2 delta T. If change of internal energy means change of temperature, all the rest, the number of atom, all is the same. Okay, we got this, right? We also can write this as 3/2 and K. This is a final temperature T2 minus T1. Right? It's like T final minus T initial. Because change of internal energy. Yeah. Similarly to this one, is like U final minus U initial, or we can say U2 minus U1, like that. Yeah, something like that. Yeah. So this one become T2 minus T1. Okay, good. What's next? Okay. So we got the change of internal energy already just now. It give us 1.6 exponent 3, right, Joel? This one. So we can put in this value, put in this value. Put in that value. 1.6 exponent 3 joule. We got the change of internal energy of helium. Okay. And then number of atoms, we got the total atoms, right? We got the total atoms, which is 1.2 exponent 24. That's what I like. You see, I like when we gather all the information here, easy for us to retrieve, no need to find from the questions. Understand? No need to find from questions. My work is systematic, and my result also become good. Yeah, if I systematic work. Okay. So I can just take from here 1.2 exponent 24 joule, 24 atoms. Okay, just put that one, that value. And I can find temperature. You see that? I can find temperature. Okay, 3.3 over 2. So total atoms is 1.2 exponent 24. And then what about the K value? K value we find from list of constant. From our list of constant, K value is called the Boltzmann constant, which is 1.38 exponent negative 23. 1.138 to 23. 138 negative 23. Okay, is that correct? Negative 1.38 negative 23. 1.38 negative 23. That's correct. Okay, so what's the final temperature? Final temperature is 315. 315. Put 315 and then minus T1. Okay, again get my T1 temperature. Okay, it will help me in the long run if I know this. Okay, let's calculate. Okay, let's calculate. 6 exponent 3 by 2 divided by 3 divided by 1.2 exponent 24. And then divide again, 1.38 exponent negative 23, and then 315. Okay, I got, okay, minus the answer. I got the temperature one is 250.5878. Kelvin. I got the temperature already for T1. Okay. Write that down. Write that down. Once you have a new information, write that down in your tables, because it will help you. So I got the temperature one here. I got the temperature one here is 250.5878 Kelvin. I got that already, right? So what's next? I need to find what? I need to find the pressure of helium gas. So pressure of density of helium gas. How to find the density of helium gas? I'm going to do that. Density. Do you see something? What I see? Okay, do you see something that I see? Volume. You see that? Volume is constant for both because it's sealed cylinder, right? Volume is constant. Okay, so this volume is constant. We need to find out this value, volume. How are we going to find out volume? Because once we know volume and we also find the mass, we just use mass divided by volume, we get density. Okay, so don't think about so much. First, find the volume. How to find the volume? Very simple. Okay, this one, look at condition 1. Okay, look from condition 1. We already have the pressure, temperature, number of atoms. We just need the volume. So we can use PV equal to nRT. PV equal to nRT. This one is the first condition. Okay, take all the values from the first condition. So we put this as pressure 1, volume is constant, yeah, and then nRT, but we have the total atoms, right? And then better we use nKT, yeah. So this is temperature 1. So we change the formula a bit, becomes PV equal to nKT, because we want to use total atoms instead of number of mole. Okay, so this pressure 1 and temperature 1. The volume is constant lah. The volume is constant, so no need to write the subscript. Only write subscript. Only the pressure and temperature is different from both conditions. The volume is constant. Okay, highlight that. Volume is constant. You see that? Because it's sealed cylinder. Sealed cylinder. Okay. So now, let's find out the volume. Okay, substitute the 1.04 exponent 5 Pascal multiply volume. Total atoms we have 1.2 exponent 24. Okay, and then K value just now we got already. K value is 1.38 exponent negative 23. Put that down. Okay, temperature, okay, 138.23. Temperature is 250.5878. Okay, so let's calculate. Yeah, let's calculate. This volume is constant for both conditions. Okay, or apply 1.38 exponent negative 23 multiply 250.5878 and divide by 1.04 exponent 5. Okay, so my volume is actually 0.0399. Yeah, meter cube. I got the volume already. So I write that down also. Okay, and this volume is the same as V1 and V2 because they are sealed cylinder. Sealed cylinder, constant volume. Okay, it's constant. The volume is constant. So okay, write that down here. 0.0399 meter cube. Okay, I got my volume already. So what's next? I need to find mass. Once I know mass, total mass, I can find density, isn't it? So it gives us a molar mass, right? How can this help us? Molar mass. Molar mass. Okay. Molar mass is mass per mole. So how to find the total mass? How to find the total mass? Total mass is just take the number of moles multiply molar mass, isn't it? So first of all, we need to know how many moles is this total atoms. 1.2 exponent negative exponent 24. So what we do is, you learn about this thing. You see that? We want to find total mass of gas. You just take the molar mass multiply by number of mole. Then you get the total mass. Understand? Okay, so you just take number of mole multiply molar mass. You get the total mass. So I need to find the number of mole. How to find the number of mole? It already give you the total atoms. You see that? It give you the total atoms. So you just divide these total atoms by Avogadro number. You can get the number of mole. You see that? The total atoms. The total atoms is actually the number of mole multiply Avogadro. Okay, so I get the number of mole first. First I want to get the number of mole, which is the number of mole is take the total atoms divide by the Avogadro constant. This is the number of atoms in 1 mole. This is chemistry, you understand? Chemistry. So, okay. So the total atoms I have now is 1.2 exponent 24. So 1.2 exponent 24. Divide by Avogadro constant. Avogadro constant can get from list of constant. List of constant, Avogadro number. Where's my Avogadro number? Na. Do I have Na? Avogadro. You see, Avogadro constant is 6.02 exponent 23. 602.23. 602.23. So divide by these atoms. So what we get? I got 1.9933 1.9934 9934 mole. This is the number of mole, yeah, in the given total atoms 1.2 exponent 24. We have around 2 moles there. Okay, so you can find the total mass of gas. Total mass of gas will be 1.9934 mole multiply the molar mass, which is, what's the molar mass? I already changed to SI unit, right? What's the molar mass? 0.004 kilogram per mole. Must change to kilogram, cannot use the gram. Change to kilogram. 0.004. Okay, write that down. 0.004 kilogram per mole. Multiply with the number of mole, then I can find the total mass. Okay, so multiply. So I got okay, I got this is 7.9734 exponent -3 kilogram. This is my total mass. Okay, the next is I want to find density already, because I already have the volume, which is constant for both conditions, and the total mass is this one. So I just divide to get the density. Okay, find the density. Just take the total mass, divide by the volume. Total mass is 7.9734 exponent -3 kilogram. Divide by the volume, which is 0.0399 meter cube. Okay, so I'm good to go. Divide by 0.0399. Okay, so the answer is 0.19, or is around 0.2. It's around 0.2 kilogram per meter cube. Kilogram per meter, 0.2 kilogram, 0.2 kilogram per meter cube. Okay, so is that correct? 0.2? Yes, that's fantastic. I got the answer correct. 0.2 kilogram per meter cube. 0.2 kilogram per meter cube. That's correct. Okay, so you see, there's some truth in my word. Always do your work systematic work. Always will be successful. You see that? I get the answer because I do step by step. I don't do a messy work. You see that? I get 0.2. So that's correct. Okay, that's for question 1. Question A. Now question B. This is just for question A. Now question B, find the final pressure of helium gas. This is easy. Find the final pressure. We want the final pressure of this one. So it's easy. We can just use PV equal to nRT or PV equal to nKT. We also can find pressure. If we want to use the the pressure law, also can, because the volume is constant. So question B got 2 methods. Question B got 2 methods. You can either use the PV equal to N, you want to use number of mole. The total atoms also can. PV with NKT or PV with nRT also can, yeah, because since you already have the number of mole, right? You also already have the number of mole. You also can use the number of mole, yeah, instead of using the total atoms. So you want to use NKT or nRT also can. Okay, just make sure since you are finding the final pressure, this one, the pressure here is pressure 2, this one is temperature 2. The rest is the same because the volume is constant. The total atoms also constant, yeah, because it's sealed. The gas cannot go anywhere, the helium cannot go anywhere, no extra helium coming from outside, and the helium inside also cannot go out. So the total atom is still constant. What changes is just the pressure and temperature. Understand? Or you want to use the number of mole also can, because we already found out the mole. Number of mole is around 2 mole. Okay, you want to use this also can. So up to you. You want to use big N or small n. Big N also have, small n we also have. Okay, just make sure the pressure and temperature, you use the second condition, not the first condition, because you want the final pressure, not the initial pressure. Okay, final pressure. So this P2, T2. So maybe we can try it out. Yeah, can try it out and see. So let's say the final pressure, we want to find the final pressure, right? Final pressure. So volume is, I got just now 0.03, 0.03, sorry, volume is 0399. Okay. I use the total atoms here, yeah. This one, you want to use this one also can, yeah. Number of mole also can. So I use the total atoms one, yeah. I use the total atoms and see what do I get, yeah. Okay, the total atoms is 1.2 exponent 24. Okay, what's the value of K? Value of K you can find from list of constant, 1.38 exponent negative 23. Okay, way 1.38 exponent negative 23. Got. And what's the temperature? Temperature is 315 Kelvin, and that's the final pressure. So let's calculate, yeah. Okay, my pressure is 1.31 exponent what? Exponent 5 Pascal. Is that correct? Is that answer correct? Yeah, that's correct. Pressure 2 is 1.31 exponent 5 Pascal. That's correct. Yeah, that's correct. So you can write down here my pressure. I got what? My pressure 2 I got 1.31 exponent 5 Pascal. Okay. So if you look at here, you see that the temperature increase, the pressure also increase. So it's correct with our conclusion, and we got the pressure, the temperature increase, pressure also increase. You see that from 1.04 become 1.31. When temperature increase 250 become 315, the pressure also increase. So it is pressure law. Since the volume is constant, this is we say this is a pressure, or we say it's a Gay-Lussac law. Gay-Lussac law. This for volume constant concept. Isochoric, yeah. Or we can say we use the formula P1 T1 equal to P2 T2. We can say when the temperature increase from 250 to 315, the pressure also will increase. Yeah, when we heat up the gas, the temperature increase, the pressure of the gas also will increase. So yeah, correct. It's tally with our answer. So you also can use this formula to find the value, you know. You can also use, you know, we can also substitute, you know, pressure, the temperature, and find the pressure. Yeah, this is the another method to no need to use the PV equal to nRT or nKT. We also can use the pressure law to do the questions. There are many ways to do the question. You see that? Make sure this must be Pascal, or in SI unit is 250.5878 Kelvin. This one is, so we want to find the pressure too, and then temperature is 315 Kelvin. Just make sure this one all in, especially the temperature cannot be degrees Celsius, must be in Kelvin, must be all in SI unit. So this one, this one will also give us the same value. Pressure we also will get 1.31 exponent 5 Pascal. If you don't believe me, you can try it out. Okay, you still get the same answer. Instead of using PV equal nKT or nRT, you also can use this pressure law to do the questions. Okay, so I think that sums up the whole questions. Very simple questions if you do it systematically. All right, thank you and bye bye.